Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, October 27, 2023. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a warm full moon evening in my hometown of Rockport, Massachusetts. These Earth and Space Reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our life-sustaining biosphere, and who wonder about the greater cosmos and all that it has engendered. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on Cape Ann's community access cable television channel, hosted by 1623 Studios. I'm grateful for the continuing interest and support shown by Rockport educators and students, Cape Ann cultural colleagues, cohorts of the Gloucester Area Astronomy Club, sundry Earth and space scientists, educators, and communicators around the world, far-flung friends, family, and other curious folk. Thank you for your active participation, comments, and general encouragements. For this 43rd episode, I will serve as the Rock On Tour, and so will need no further introduction. Yay! My topic for this evening is sensing the biochemical character of galactic ecosystems. That's quite a mouthful, so I'd better get on with the show. So now I'll share my screen. Okay, I want to start. Slideshow. Beginning. Okay, everything should look pretty good now. Let's see if we can find the speaker here.
Yeah, it looks good.
Okay. Okay, looks good. All right. Well, I don't want, I want just speaker. Oh, wait a second. Well, okay, we got Arthur. Okay, so I'm going to start with a question. And it's, what if we had big enough and sensitive enough noses to find out what our Milky Way galaxy smelled like? That might sound like a fool's errand, but we have already made some significant strides courtesy of the meteorites that we have collected here on Earth. Consider the carbonaceous chondrites that comprise about 5% of all the meteorites that have impacted Earth. These stony meteorites are rich with tar-like hydrocarbons. If you could get your hands on one of these dark rocks and heat it, you likely would be able to smell the pungent organics. Just think of fresh asphalt. So other people have weighed in on what the Milky Way might smell like, including astronauts who've gone out of the space station and gone back into the International Space Station. And they cite having smelled hot metal, gunpowder, rotten eggs, and bacon. Other people have suggested ammonia, ozone, brake pads, and also walnuts. So kind of crazy. So let me move on. I think first I should note that the happy hunting grounds for finding these sorts of compounds can be found within the galactic ecosystems that roam the Milky Way. And so now I need to let you know what a galactic ecosystem is, because it's not as popular a term as it could be or should be. And so here's a very simple definition of what a galactic ecosystem is, or systems are. Self-gravitating regions of gas, dust, and newborn stars. Some people call them star-forming regions. And they include dark clouds, molecular clouds full of molecular gas, very cold molecular gas, and dust, which makes the clouds look dark. But depending on the scale, you can also get ionized regions that have been ionized by hot stars that were formed, hot massive stars formed inside the molecular clouds. Those are called H2 regions, And the 2 refers to the fact that the hydrogen has lost one of its electrons. It got zapped away by ultraviolet photons from the hot stars. And on even larger scales, you can get downright starbursts where you add more energy courtesy of massive stars that blow up. And so that gets to the second definition, stellar feedback. Depending on the scale of your galactic ecosystem, you can have ultraviolet radiation, winds, and supernova blasts from the newborn massive stars. But even without the massive stars, you can get winds from newborn lower mass stars, all of which can transform the architecture of galactic ecosystems while transmuting their chemical makeup. The ultraviolet radiation in particular can change the actual chemistry that's resident in these galactic ecosystems. And some of those chemicals can be regarded as biochemicals, and those would be the molecules that play key roles in sustaining life on Earth and maybe elsewhere. We have a myopic view of what a biochemical is, but at least here on Earth, we know that water, H2O, is important. Formaldehyde, H2CO, is important. Molecular oxygen, O2, and methane, CH4. Hydrogen cyanide turns out to be especially important, as I'll show later. Ammonia, NH3, phosphate, PO4, various amino acids, which have nitrogen in their base, the nucleotides that go into the double helix of DNA and the single helix of RNA, and those are useful. Those are the molecules that are responsible for reproduction, the programming of reproduction, and also for making proteins. Okay, so those are the definitions. I'm gonna go back. I seem to be stuck. Hold on. Stop share and go back. From current slide. Okay, here we go. Okay, so here is the raft of molecules that have been detected basically as of a year ago, approximately a year ago. And there's a lot of molecules, and you'll see that a lot of them contain carbon. So those are what would be regarded as organic molecules. And you can start with the 2 atoms, and where you have molecular hydrogen, which is the most common molecule, and CO should be here somewhere. But I have names later on, so I'm going to get to them later, right? But this is just the bevy of molecules that have been found in interstellar space, in particular these galactic ecosystems, which what I'm talking about. And here a listing of molecules with names, with molecular hydrogen being the most abundant in interstellar space. Carbon monoxide is the most luminous, and that's what is often used to trace these galactic ecosystems. And I think I'm going to go to 3 atoms. Hydrogen sulfide, so they've just that's the stink of rotten eggs, which you're probably all familiar with. But also water is there, and ammonia, formaldehyde, acetylene, and anything else you like that floats your boat. There's methane, and we'll move on to more atoms. 6 atoms. Here comes 7 atoms, so you've got methyl alcohol. And if you move on to 10 atoms, you get ethyl alcohol, enough ethyl alcohol in the Milky Way to give a galaxy-wide hangover, that's for sure. Glycoaldehyde is a form of sugar. And glycine, not confirmed, is an amino acid. Then there's benzene, which is first ring molecule, C6H6, and that goes into making polycyclic aromatic hydrocarbons. Those are the PAHs. And how that happens is the benzene rings get woven into mats of flexible polycyclic aromatic hydrocarbons, and they tend to smell a lot like the smell of a charred burger or the back end of a diesel bus. So I just want to note, in case I didn't catch these molecules, there's also acetone with its fruity but toxic odor, ethyl formate that smells like rum, the sugar glycoaldehyde, which I mentioned, the cyclic ring molecule benzene, and all the polycyclic aromatic hydrocarbons that have been found in space. Just pretty amazing. It's quite a bevy of complex molecules. And simulation or replication of the complex chemistries taking place have been done or are being done today in the lab, whereby they place a sample of ices in a vacuum setting, and then they zap it with ultraviolet irradiation in a process called photolysis, and they are building all sorts of complex organic molecules this way. And trying to figure out the pathways. I show this slide just because it looks so complex. Which way do these molecules go? What's the pathway towards complexity? But they make bigger molecules out of smaller molecules, and it depends on various variables, dependent variables. One of them is temperature, and so you'll get more of the product with a higher temperature, going from 20 kelvins to 70 kelvins. And then you also get more by increasing the amount of ultraviolet light impacting the ices. So they are making good progress in trying to understand the chemical pathways that might be occurring in these galactic ecosystems. And there's a claim from, I'll just show her, there we go, Karen Oberg, and she claimed in a presentation that hydrogen cyanide is a key molecule for making biologically important molecules. And so you can imagine, in the context of a planet which has water and volcanic outgassing and incoming stuff from comets, for example, and you can build up, courtesy of the hydrogen cyanide as kind of like the mediator, you can get precursors of phospholipids, and those are what the fats that go into making the membranes of cells. And you can see the P here, that's the phospho. Amino acids, which are the building blocks of proteins. And they're all nitrogen based. The nucleotides, which go into building those single and double helix molecules. And they also have phosphorus as part of their backbones. And then there's the Krebs cycle metabolites, which I don't know much about, except that these are what mediate the transfer of energy into and out of the cells. So Karen Oberg and her lab especially thinks that hydrogen cyanide is a keystone molecule. Again, there we go. Okay. These molecules have handedness. It's called chirality. And so here's, the difference between a left hand and a right hand. You can't put one hand over the other to make them match. And that's because left hand and right hand have different handedness. And it makes a difference, especially in terms of smells. An example is Carvone, or I don't know, Carvoni. But the left hand version gives the smell of caraway, and the right hand version gives the smell of spearmint. So that's because our receptors in our noses are chiral. They're chiral discriminants, handedness discriminants. And it's interesting that on Earth, amino acids such as alanine, serine, and lysine, I think all of those, tryptophan, those are all amino acids. They're left-handed, while sugars are right-handed. And we are finding that molecules in space also have particular handedness. The latest molecules to be discovered have been found in one of the nearest galactic ecosystems. It's the Taurus molecular cloud. It's a host of low mass star formation. There aren't any big stars in it, but this is what can get made in a low mass star forming region. And I don't know anything about these sorts of molecules. I get kind of a kick out of vinyl cyanoacetylene. I mean, that suggests naugahyde to me. Anyway, I just wanted to show them you have some ring molecules as well. All right. And so there's basically pathways in the galaxy into and out of galactic ecosystems where chemical evolution proceeds. So let's start in a galactic ecosystem. Here's a molecular cloud that has spawned a bunch of stars, a few of which are very massive. And so they have a lot of ultraviolet light, which will not only ionize a region in the cloud, but also will produce photolysis on icy grains in the cloud and change the molecular makeup in those ices. And some of that will be delivered to pre-planetary and protostellar systems. And so here you have a pre-planetary disk around a protostar, which then gives birth to a star, and like the sun and the planets around them. And so already the planets probably have a host of molecules resident on and below their surfaces. But then there's also delivery systems. Meteorites will impact the planet, and we know that meteorites contain amino acids. And then comets can impact the planet, and we know that comets contain ethane and acetynitrile and formic acid and other organic molecules. And probably on the planet, the larger molecules get made, the biomolecules like RNA. Meanwhile, the star will evolve and become a red giant star. And in the outer atmosphere of that red giant star, the temperatures are cool enough for certain molecules to crystallize out. And so that's where you get your dust, which then mixes back into the interstellar medium, gets collected into a galactic ecosystem, and the beat goes on. All right, so kind of neat picture. Here's not as nice a picture. And it's a Sunday Comics cartoon of basically a galactic ecosystem that has all the stuff. It's not a low mass molecular cloud. That's where you have low mass protostars with little UV radiation. You just have winds, and it's a relatively cool system. A higher mass molecular cloud would have these massive photoionizing stars. Those are these blue stars. They have not only strong winds, but they have strong ultraviolet radiation, and that radiation turns what was once molecular hydrogen into single atoms of hydrogen, and then rips the single electron off of the hydrogen. And that's what you see as those beautiful red regions in Mario Mato's pictures of nebulae and galaxies. But wait, there's more. You can have a system that the cluster is rich enough so that, and it's been around long enough for some of the stars to die. It only takes a few million years, and you can get a hot supernova. And in this area, you're going to get million-degree gas, whereas in this area, it's 10,000-degree gas. And there's a tremendous pressure placed on the region due to the super hot gas. And this is where you're starting to get what would be called a starburst. And if it's a sufficiently intense starburst, it can vent out of the cloud and produce a superwind. And so we have multiple scales for these galactic ecosystems. And I think depending on the scale, you're going to get different chemistries. So where do you find these galactic ecosystems? Well, visually, you can see the nearby clouds in silhouette against the stellar background. And so I can point out in the southern hemisphere, this particularly dark region, that's called the coal sack, and it's right near Alpha and Beta Centauri. Alpha Centauri is the nearest star. There is, towards the galactic center, there's this thing called the Pipe Nebula, and that is a region of molecular gas and dust, which I think it's a relatively low mass star forming region. I will show Ophiuchus, the Ophiuchus region, star forming region, and we'll get involved with the Aquila Rift, and then later the Cygnus Rift of clouds. And all these little red spots, this is where you have ionized hydrogen. These are H2 regions. There's a big H2 region supernova complex called the Gum Nebula in the southern hemisphere. And here's the Orion star forming region. Okay, all right. So that's what you can see visibly. You can see the nearest star forming regions and some of the nearer H2 regions. In the infrared, you can see the dust associated with all this activity. This is dust that's been irradiated by stars, most of which are hot stars, and they warm to a higher temperature and re-radiate their alarm. And you can see that the disk of the galaxy is really much thinner than what we see optically, and that's because optically we are biased towards the nearest regions. But already you can see the Rho Ophiuchus star forming region, and this is the Cygnus star forming region and the Cepheus star forming region. And I'm going to do close-ups of all of these because it's really neat. So here's the visual. This is looking towards the center of the Milky Way galaxy, with Sagittarius right near the center, and Scorpius as well. And you can see the Pipe Nebula, some H2 regions which have been highlighted. This is the Lagoon Nebula, the Eagle Nebula, and I think this is the Omega Nebula. And this is the constellation of Aquila with Altair in it, and this is the Aquila Rift dark cloud region. Okay. We're going to now go to greater galactic longitude, And oh, not yet. This is what you see when you look in the far infrared. And again, the disk is very, very thin, actually. And there's objects above and below the galactic plane. They appear above and below the galactic plane because they're actually relatively nearby. And you can do a type of image processing that allows you to highlight the enhancements and diminutions in the emission. And now you can see regions out to the far side of the disk of the galaxy, which is pretty neat. And so all that's good, happy hunting grounds for complex chemistries. The region around here, the molecular cloud region around here, Sagittarius B2, is well known for finding complex molecules. Here's the Rho Ophiuchus region and the R Corona Australis region. And what is all this stuff, this froth of material? And you can see, you get an impression that there's some loopiness going on in certain areas, like maybe partial shells here. It's like a Rorschach test. It's actually hard to figure out what you're actually seeing. But it might indicate various dynamics going on in terms of the winds and the light and the blasts from the hot star forming regions. So now let's move on. Oops, Corona Australis. I mentioned that this is a low mass star forming region. It has several young stellar objects of relatively low mass. This is a globular cluster much, much farther away. These HH objects refer to jets of material from the newborn low mass stars, and they're impacting their natal surroundings. And I can't see what the molecules are, but there have been a few detections of complex molecules in this relatively low mass star forming region. Moving up in scale, the Rho Ophiuchi molecular cloud has hundreds of young stellar objects, including some of relatively high mass. There's this nebula, which is responding to this particularly high mass star, as there's some red nebulosity here as well. And I can see that there's been some interesting molecules detected here, including water. There's new data available now at multiple wavelengths. So you start in the visible in this region, and you've got your H2 regions, M8, M20. In the infrared, you start picking up the polycyclic aromatic hydrocarbons and dust in those regions. And then in the submillimeter, you can actually see where new stars are forming, cold molecular cores. Neat stuff. All right, let's go a little towards greater longitude, and you're in Cygnus, and many of you amateur astronomers would recognize the Cygnus rift. You can trace it with binoculars on a dark, moonless night. There's a H2 region called the North American Nebula, and several H2 regions. There's the Heart and Soul Nebula in Cassiopeia. And what else do we have? Another galaxy 2.5 million light years away. Okay, so this is what we can see in the infrared. The Cygnus region is just chock-a-block with interesting high mass star formation. There's this shell of emission. I think this is the Cepheus shell. And you can see secondary star formation along along the shell. And so these are all great regions to investigate more closely. And there's another shell here. So really neat stuff. There's that galaxy. Okay, and lots of froth. I mentioned the Heart and Soul nebulae. Here's the Soul Nebula in Cassiopeia, and it has basically all four phases of matter. You have ionized matter, where electrons have been ripped off of the atoms, intact atoms, molecules, and granular phases, though that would be the dust. And so there's a cluster of stars here, and it's impacting the remnant molecular cloud, which responds in the form of resistant pillars. And you might notice that there's star formation occurring at the tips of those pillars, probably because of the pressures involved. And let's see, blue, green, and red, respectively. Blue is stars. Green is the polycyclic aromatic hydrocarbons. And red is the star-warm dust. So this is a rich hunting ground for chemistry as well as physics. Okay, going further to greater longitude, looking towards the galactic anti-center, there's the familiar Pleiades star cluster with a small H2 region called the California Nebula. And where's Taurus? Oh yeah, Taurus. This little region is the Taurus molecular cloud. That's where they found all those complex molecules. It can only be seen in silhouette easily. And then there's the Orion star-forming region, which is the nearest site of burgeoning massive star formation. And so that's what I'll focus on, I think, a little bit. Here's the infrared spatially filtered image, which shows the Perseus star-forming region. So it's very bright. This is the shell surrounding Lambda Orionis, the head of Orion, and then there's the region around the Horsehead Nebula and the Orion Nebula itself. So it's a busy area. These are all great regions to investigate, to see what they have in them. And then I think this is completing the tour of the Milky Way. There is this large H2 region supernova remnant complex called the Gum Nebula. This is in the southern sky. Carina Nebula, which is the biggest, brightest H2 region in our galaxy. The coal sack, as I said, is a nearby molecular cloud. And I think that's all I want to say here. Let's go to the infrared. The Carina star-forming region is actually more extensive. And if there is evidence for venting, this might be it. This plume, this curved plume of enhanced emission from star-warm dust. So pretty neat stuff. In case you're wondering, that's missing data, this little wedge. Okay, so we've done the tour. Lots of places to go check out. Beyond the Milky Way are other galaxies, including a companion galaxy, the Large Magellanic Cloud, and it has the biggest, brightest H2 region in the local group of galaxies. This is the Tarantula Nebula, and it's a real barn burner, and it also has multiple phases of matter in it, and there might be some very interesting chemistry going on there. Here it is in the infrared, and it's color-coded in the same way as the other Spitzer Space Telescope images, where the green indicates polycyclic aromatic hydrocarbons, and the I think the brown and the red indicates star-warm dust. So you can see that there's lots of complex molecules amid the dust grains. Pretty neat stuff. A distance similar to that of the Andromeda galaxy is the Pinwheel galaxy, M33. Seen here at visible wavelengths, it just looks like a ragged spiral galaxy. It has the second largest H2 region, NGC 604, and that can be tracked to this Herschel Space Observatory image in the far infrared. I think it's this region right here. But you can see where the star-forming material is more congregated towards the spiral arms. The spiral pattern involves thinner arms, and this is where the molecular gas is congregated and where stars are forming within this pattern. Pretty neat. But new is what has been seen in a galaxy which is basically 10 times farther away, and it's called the Phantom Galaxy. So we'll look at this in honor of Halloween. The radio emission, as detected by the ALMA Observatory in Chile, shows the spiral arms very nicely, as does the dust lanes in the visible light picture. Shows the spiral arms rather nicely. But this is the nexus for all the star forming activity. This is where the galactic ecosystems have congregated along these exquisite spiral arms, probably shepherded by various kinds of physics, including spiral density waves. And but what's new, well, the ALMA view is pretty new, but what's new is what James Webb has shown. Just exquisite pattern of interarm material. So this would be emitting dust and molecules. I checked out the wavelengths, and this image includes wavelengths which would pick up the pause, and wavelengths that would pick up the star-warm dust as well. So it's just exquisite, and I'll get into this a little later. You can start seeing the hints of a cellular structure when you combine the Hubble and the Webb views. The Hubble provides where the star formation is most intense, which of course is near or adjacent or in the arms. And then there's kind of like the just fabulous cellular structure. I wouldn't call it a web. I kind of just call it cellular, and what is making these cells. And here's an enlargement. Wait a second. There we go. Here's an enlargement.
Wow.
Yeah, and I artistically, this is just knocks me out, and it makes me wonder what the heck happened here. Was it an explosive event? And now we have secondary star formation along the rim, or what has caused this cellular structure? And I hark back to the froth in the infrared images of the Milky Way, because a lot of the froth has similar shell-like structures, but that's just a thought. And here are the H2 regions, which are kind of like blossoms on a branch. Timothy Ferris had that in his book. Okay, but we're not yet done. We're close. This is a much closer galaxy, M82. We're back to around 10 million light years away. But this is a small galaxy, a much smaller galaxy than M74, but it's completely overtaken with starburst activity. Something happened in this core area of the galaxy, seen edge on, to produce an incredible amount of stars, including massive stars, some of which are photoionizing gas, but some of which have exploded and produced this incredible wind, bipolar wind, which includes hot gas as well. So it's evacuated a region which can now be illuminated by the remaining hot stars. And so here's a cartoon of what we think we're seeing. You have entrained cooler gas, and the blue is the X-ray emitting plasma, and is regarded as the starburst region. This is what you would see if it was face on, but what you're actually seeing is from here. This is where the eye would be. We're seeing a edge on, nearly edge on situation. And so this this particular galaxy has been observed and found to have some very interesting molecules as well. And it makes me wonder whether there is a sweet spot in terms of scale and intensity when where maybe when the intensity gets a little bit too much, the molecule building is unable to proceed further. But that's a question which needs to be addressed by people who know more than I do. So I think that's it. Okay. And how you can find out is to survey these galactic ecosystems. And the best instrument for that is the Green Bank Observatory in West Virginia. That, for example, was the discovery machine for those big molecules recently found in the Taurus molecular cloud. And here's what it takes to try to discover a new species. You're not suffering from a dearth of data. There's molecular lines, emission lines all over the place. And trying to figure out what the pattern, what pattern goes to what molecule is that's beyond my ken. In Europe, there is the 30-meter diameter dish. Where is this in Spain? IRAM dish. And then there's this NOEMA array, I think, in Europe as well. And the surfaces are smooth enough to get down to sub-millimeter wavelengths where a lot of these molecules are emitting. And then in South America, there's ALMA, the Atacama large array, large millimeter array, yeah. And this has been doing just amazing jobs, not just detecting various molecular species, but also mapping exquisitely. And the future is happening in the Southern Hemisphere as well, in Africa and Australia, with the square kilometer array. I think this is the one in Australia. And this has great potential. And so that's pretty much it. I want to thank Brett McGuire, Karen Oberg, and Christina Tremonti for my use of their presentation slides, which occurred at a meeting of the American Astronomical Society. And I also want to thank Mike Deneen, who provided this fabulous photo of a hamburger with charred meat that's redolent with pause. All right, that's it. And I will now stop the share and get you guys back. And feel free to unmute.
I got two questions.
Yeah, I'm ready.
What do you have any knowledge of what Fermi bubbles are?
That's a galactic topic. The Fermi bubble is something that has been seen towards the galactic center, and it's very hot gas, bilobal, but I did not do a good job. Bilobal, coming above and below the galactic plane, and it's observed in both gamma rays and X-rays.
So it's a hot plasma?
Yeah, a wicked hot plasma.
And the other thing is you have a lot of H2 regions.
Yep.
And you said hydrogen with 2 electrons. So hydrogen is no, correct.
One electron that gets ripped off. Roman numeral 1 is an intact hydrogen atom. So that's and so according to the parlance, Roman numeral 2 is hydrogen with its 1 electron removed.
So it's ionized.
Ionized, that's right.
Okay. Okay, that makes sense.
By the presence of those hot stars.
Sure. Thank you.
Sure.
Oh, great presentation.
Dick.
Bill, you've mentioned dust several times.
Dust.
What is the composition of this stellar dust, interstellar dust?
Typically silicates or graphites. So
and cat hair. Don't forget cat hair.
Cat hair. Dander. It's actually a lot of dander.
Under my bed.
Yeah, I'm allergic to it.
And this is the product of novas, or?
Yeah.
No, it's from, they think it's the evolution of stars, regular stars like the sun.
Yeah.
They go through a red giant phase, and the outer atmospheres of the red giants are cool enough for whatever silicates to crystallize and graphites to crystallize. And then that gets blown out into the interstellar medium and becomes one with the gas, and various physical processes will gather the gas until gravity has its way, and you end up getting a star-forming cloud full of dust.
And it ends up on my car hood every week, right? The silicate, the graphite.
Well, bird crap.
I actually tried with a group of kids in Maryland back in the 90s to collect some of this cosmic dust. And I can't say we succeeded. We succeeded in collecting soot from the combustion furnaces in the school. So it's tricky business. You want to do it when their pollen's not flying.
Yeah.
And so you do it in the wintertime. But I had the collection on the roof of the school, which was the best part for the kids because they got to go up on the roof. And but when we looked at the stuff through microscopes, there were no spherules, which would have been an indicator of cosmic dust, or taking a magnet and seeing if you could find some meteoritic material.
You'd use HEPA filters to catch it?
Used trays of water, and the stuff would slowly settle to the bottom.
Or slabs of aerogel. Flap your arms very quickly.
Have you ever handled aerogel? It's amazing. I mean, it's so insubstantial. It's just incredible.
It's smoke, solid smoke.
Yeah, solid smoke, exactly. So
you answered all my questions, so thank you.
Yeah, I think the future is bright for cosmochemistry. I think another major question is, what gets transferred from the cloud to the planet? I think that's, what goes into the planet intact, what gets transformed in the transfer. Because a lot of people think that cosmochemistry is a planetary process, but I'm arguing that there's a lot going on in the clouds, and you can detect more in the clouds because they're bigger.
Hey, Bill,
Yeah.
I do have a question on a serious note. Why do molecules or atoms travel in herds? Why aren't the galaxies homogeneous? Why are there H2 regions at all?
Oh, the orchestration of structure.
Yeah,
That has to do with what's going on in the galaxy. And in big disk galaxies, you have shearing in the disk, and that shearing is, and the disk itself is susceptible to instabilities. And
why would all
spiral
the
density waves.
ionized hydrogen gather in a one lump?
Oh, that's because there's stars, hot stars right there. Wherever the hot stars are, well, they tend to be in the clouds from which they formed, and
Right.
and then they zap their surroundings. They're not too nice to their wombs.
Are they as homogeneous in the group as they look through a telescope? Is it all hydrogen ions? Is it all H2?
No,
Or is
it's
it
multiple
as
phases. Yeah, you
lots of pause and thises and
yeah,
that's and
and cavities, and the molecular clouds that host them themselves are
Yeah.
filamentary. Somebody said the insides of molecular clouds are full of outsides, like that.
That galaxy looked like Swiss cheese with all the bubbles.
Yeah, like what?
Swiss cheese.
Swiss cheese. Okay, all right. Cellular. Yeah, it's a churn and earn a burn and funk.
Wow.
Hello, Bill.
Hello,
This is
Chuaji.
no really. Yeah, how are you?
What fine? What time is it?
I managed to stay up. It was just by chance that I saw the email in at the right time when I was almost ready to go to sleep. I said, well, let me just listen to this. Very interesting talk.
Thank
and
you.
really something very different from the physics that we do, that we think about every time.
Right.
So when we talk of analysis of data, we are talking of spectroscopic analysis, I suppose.
Exactly.
So when you say all this data is available, is the training material or the software and all that like some place where there is a portal where we can go and learn and understand how to use the data where independently, or
that's a
we have
very
to
good
go and-
question. Chuaji, coming to us from Tanzania.
Yes.
And
3 o'clock at night here.
yeah.
Whoa.
Good heavens. And I know in the United States that there's training associated with the radio telescopes, and there's workshops that are associated with it. In Africa, you guys are coming online with some really good instruments, and I know that you're well connected to European astronomers, and I'm just hoping that you're going to get the training that you deserve.
We need that. Yeah, we certainly do.
So
it will be very useful to get the chemistry line also going here. That's my point.
Right. This is chemistry, which
really.
The last time I took a chemistry course was in high school.
Well, and the biology, which is then connected. By the way, when where you mentioned a lot of these organic molecules, that means there will be other molecules besides these, isn't it? Besides the organic molecules.
Right. For example, hydrogen sulfide, H2S. That's the one that makes the stink of rotten eggs.
Yeah.
So yeah, and water. Water is not.
No, but my point is that predominantly are these carbon based only, or are those more stable?
Carbon is a very promiscuous molecule. I'm sorry, atom. It has 4 electrons in its outer shell, and it wants 4 more. And it allows for abundant
Lots of
bonding. And so
Right.
we think we know why the most complex molecules are loaded with carbon.
With carbon. Okay. So
The ring molecules,
we
The
should
ring-
expect a lot of carbon molecules in space. That is the
yeah,
idea.
and we're discovering it. And those ring
Right.
molecules are the
Yeah.
corners of the ring
Yeah.
have carbon. It's a ring of carbon
Yep.
with usually hydrogens hanging off
Yeah.
in the ring.
Okay.
So
Great.
and carbon
Very
chemistry, I
interesting.
mean, that's organic chemistry. That's the course that gets rid of so many students.
No, but we had a very good teacher, at least at high school level, So I remember, some very good mnemonics where you could predict the structures very easily and all that.
Uh-oh.
I'm off it at the moment, but I think organic chemistry is quite interesting. Thank you. It was a very nice talk. Thank you.
Well, I would certainly encourage your students that you have contact with. I know
Yes,
you're a mentor for so many.
I'm trying to do that. Yes.
Yeah.
Thank you.
Any other comments, questions?
Gee, with all
I
those.
think a course in organic chemistry statistics would pretty much clear the whole population right out.
Sounds like a
Yeah.
job for AI.
Yeah. Now,
Organic chem is a great course.
AI will
Not bad
will help
mouthing
a
it.
lot.
What'd you say, Mario?
I said organic chem was a great course, and stop bad mouthing it.
Okay, but I think I'm accurate in saying that it's a great
Stuff.
I loved it.
It's very complex. Yeah.
Well, you ended up in the medical field consequentially.
You think with all those organics, we'd have more potential for life.
Yes, that's
Mhm.
that's the thing, to get those
Yes.
those biomolecules.
Mm.
I'll be curious when they find out what's coming off of the water and the ice off of the Jupiter moons.
Yes.
60-mile
tuned.
deep oceans got to have something.
We'll try to get some speakers on that.
Get some samples.
Get some samples. Speakers with samples.
Yeah.
Okay. Thank you all, and happy Halloween.
Yep.
Thank you very much.
Think about the
All
fate
the
of the
best.
galaxy.
And you can
Thank
get
you.
off the
Bye.
costume. Take off the mask.
Thanks. So long.
Have a good night.
Bye.
Bye all.
Good night. Bye bye.